Transactions and blocks. Now, a blockchain, we have an initial block that we call the genesis block. And it has some sort of a hash seal that we've put on it. Okay, we've got a hash down here. And that's our first block. And then at a later point in time, we communicate this with all the other nodes. They all agree that this is the correct hash. We add a new block to this. And that block has in it this hash value. So if this is 42, it's got the 42 in it. So essentially it acts as a pointer back to that block. Now it's got some other things in it. Some transactions. We're going to look at what's in the transactions. And then it's got a Merkle hash. And then it's got a seal. Let's say that this seal is 81. So we've got an 81 here. And we're the person that found it, so we transmit this out to all the other nodes. They all agree 81 is the solution. They say yes. And a little bit later, we add another block that has in it the 81, which is a pointer back here. And the 81 now has transactions in it. And we go out and we do a Merkle hash to get validity of those transactions. These pieces, the 81, the transactions, their position, this all goes into this hash, and let's say that we get an A2 for this block. Now in the land of Ethereum, this is happening every 22 seconds. New block is added, new block. In Bitcoin, this is about every 10 minutes. But either way, this is what's in the blocks, and we're going to look at the blocks, how we guarantee the order, the Merkle, where the hashes go, and we're going to look at the details of that. But this is what's in the blockchain, and this is the chain, is each block has the hash of the previous block. So if you wanted to go out and change this block out here, that means you don't have to just change this one because you're going to get a new hash here. If you want to lie and cheat and change it, you're going to have to change this one, and you're going to have to change all subsequent blocks. Because every one of them, let's say you want to change this to B2. That means that this changed. That means that this changed. That means that this changed. All the way down through the blocks. Now, the proof of work algorithm basically says, I spent a lot of effort in coming up with this 81. And if you're going to change it and cheat, then you're going to have to put in that much effort to be able to fake it. And right now, that's running about 11 million an hour. Okay? So you can just go back in time and say, at any block, if I wanted to change it, the cost of electricity to recompute these hashes, to find them, to cheat and falsify this information, this is what it's going to cost. Couple $100 million a day. And that's not the hardware to do it. That's just the cost of electricity going into these blocks. Now, of course, there is this factor too. We have, coming out of this, we have a machine over here that's producing the electricity. Okay? And that machine producing the electricity is producing these bad effects. So there's pollution coming out of this because we're using up gobs of electricity. So we'd like to be able to do something else besides this, but right now we've got roughly this much going on in Bitcoin. We've got about the same thing going on in Ethereum. And we'd like to go to a different system maybe that does the security but doesn't have these flaws. But this is what's there. There's some blocks. Each block happens at a fairly predictable amount of time. In each block, there's a bunch of transactions. We take the information together, we serialize it, we Merkle tree hash it, we hash it over here, we get a seal for the block. If we're the person that found the seal, we get a little reward. We get one of those. And yes, This is how you participate. Now, this process of producing seals on blocks over time, that is mining. Okay? You're doing the work to find the magic piece that says, here it is. And when you do the mining, you spend expenses, you have to have a reward to justify your hardware and your time. That is the reward that gives you the little smile. Now, the other thing that could give you a smile, and this is becoming more and more true, is transaction fees. As time goes on, it gets harder and harder to mine Bitcoins, and eventually they will all be found, and you will no longer get it from mining in that form. You'll get it from transaction fees, where you're charging people to put their transaction into the chain and calculate the seal for it. So this combination of building these things is what's going on. Now, why is there security in this? The biggest security comes from game theory. That yes, the incentive for people to do it right is there. They get a reward. It's easy to check if they do it wrong. If they lie, it's easy to figure out. Okay, so that's quick. It's slow to calculate. That's proof of work. Now, in proof of stake, what you've basically said is, I'm going to post a bond up here. I'm going to say, if I do a bad job, you take my money. And you say, here it is. And the bigger my pile of money, the more work I get, the more times I get to be the person that says, yes, I'm going to put my stamp of approval on this. And instead of spending all this time and energy out here doing work, I'm just saying, yes, I'm the person that got chosen, and I can prove it over here. Here's my signature, digital, and here's my seal for this block. IOHK's Cardano and Ethereum 2.0 are both proof of stake. They're second generation systems that avoid all of this pollution and stuff over here. And the question is, are they fair and secure? IOHK has done mathematical proofs on security, and they're improving what we would consider the fairness of the system so that everybody that participates with a node gets rewards and gets results from doing that. There is a third generation called Honey Badger. Honey Badger is a cryptographic solution that, instead of relying on posting a bond, says, we will do this work and we will cryptographically be able to hide the future so you can't cheat. And when we reach this consensus agreement between these people, at the moment of consensus, you all have the information, you can all see it, and you can all produce the seal. And so there are cryptographic solutions. The cryptographic solutions is something I've been very interested in a long time, but that's kind of a third generation. And there's good mathematical proofs coming out of a number of places like Carnegie Mellon and Berkeley that the cryptographic solution actually works. But, it is mathematically complex, much more so than these other solutions. So this is where we're at right now, is there are proof of work and proof of stake systems that are real and live. And let's actually go poke on the computer and let's take a look at the details inside these of where's the hashes, where are the fields, where are the blocks, what are the transactions, what's the data structure that is involved.